In this video, we're going to learn about the concept of refraction. We've been focusing on reflection so far, and now we're going to examine another behavior of light called refraction. We'll see how it works, and we'll see how refraction is related to the speed of light. Following this presentation, which is part 1 of refraction, we're going to go and take a look at part 2 of refraction by examining ray diagrams in more depth, and then we'll take a look at part 3 of refraction, which is the application of refraction and a concept called total internal reflection. But right now, this is part 1, just a basic introduction to refraction and how it relates to the speed of light. So here we can see an example of refraction occurring. It's one of the most common examples that we often cite in physics. And by the end of this presentation, you should be able to explain this picture, what it means and what it represents. For example, you can see light rays from this fish over here exit the water and go into the air. So it exits the water over here. It goes into the air, but you'll notice as it goes into the air, it bends. And so your brain sees an image coming from over here rather than where the actual fish is. So again, by the end of this presentation, you'll be able to explain why that actually occurs. The main topics for the refraction presentation include a review of the behavior of light that we studied in this unit, what refraction means on a conceptual level, how it relates to the speed of light and the index of refraction, and then we're briefly going to enter the Snell's law conceptually, and that's in part 2 of the refraction presentations. Following that, we'll enter into part 3 of the presentations, which is application of refractions, including the critical angle and total internal reflection. So these are the various behaviors of light that we've studied so far. We studied transmission, how something goes through, how light rays go through a material, and sometimes when they go through a material, they can bend. And so that would be called refraction when they go through and bend. We saw reflection, where light rays hit a surface and simply bounce off that surface. We also saw absorption, and I did mention diffraction in a previous PowerPoint. Today, though, our focus will be on the refraction behavior of light. Once you completely understand refraction, you'll be able to understand how rainbows form. You'll be able to understand why when light goes through a raindrop or a prism, the white light actually separates into its various colors of the visible spectrum, the Roy G. Biv. So by the end of this presentation, you'll be able to understand how refraction plays a role in the formation of rainbows through prisms and through raindrops. It's not diffraction, it's refraction. Diffraction involves little slits, like in the little diffraction goggles, but in the case of refraction, there's no slits involved. It's simply the bending of light as it goes from one material to another. So you already know that light travels in straight lines. Now, when light travels in straight lines, sometimes it can go from one material to another. So for example, we might have light starting off in air, and then it might go from the air into the water. Now, when that happens, that will cause the light ray to bend. So when light rays go from one medium to another, they will often bend. They can bend towards the normal, as you see in this case here, and sometimes they can actually bend away from the normal. But the whole point is that when you go from one medium to another, light rays can bend. And medium just means a material in which light is traveling through. The plural would be media. So I'd say air is one medium, air and water are media, if I were saying the plural. So now we're going to see why is it that light bends when it goes from one medium to another. And it all relates to the speed of light. As mentioned in the introductory PowerPoint to optics, light travels very, very, very fast. It travels at 300 million meters per second, written in the scientific notation format. Please review that if you don't remember how to use that format. Written in the scientific notation format, it is 3.0 times 10 to the power of 8 meters per second. So that's very fast. At that speed, you can travel around the world 7 or 8 times in 1 second. So that's the speed of light in space, where there's very, very, very few particles and light can travel at its fastest. So what that means is when we say the speed of light, in reality, the speed of light actually depends on the medium in which light is traveling in. Light travels at its fastest in space because there's nothing in its way. But once it enters air or water or diamond or honey or other media, it will travel slower because it's slowed down by the particles of the medium in which it's in. So as mentioned, light travels at different speeds in different media, and that's because there's more particles in certain media than others, and as a result, the light will slow down. So in this picture here, you can see light waves traveling in different media, in empty space, in air, in water, in glass, and in diamond. And the idea is that the light wave is traveling from the source to a sensor. And what you'll notice is the highest number for the speed is when light's traveling in space. However, when light goes through something like diamond, it's a smaller number for the speed, meaning it takes more time for light to go from the source through diamond to the sensor than it does through something like space or air. Water is slower than air. Glass is slower than water. Diamond, the speed of light in diamond is slower than the speed of light in glass. So different media have different speeds of light. A medium where light travels slow is called a dense medium, or an optically dense medium rather. So an optically dense medium is a medium where light travels slow compared to another. So for example, I could say that diamond is more optically dense than crown glass. I could say that clear water is more dense than air, optically dense speaking. I can say that air is more optically dense than space. So the slower light travels in a medium, the more optically dense that medium is said to be. So now we really have the answer to our question as to why light bends when it goes from one medium to another. The reason that light bends when it goes from one medium to another, so for example, here we have a light ray starting off in air, it goes into glass and it bends, is because there's changes in the speed of light as you go from one medium to another. The fact that light slows down or speeds up as it travels from one area to another, one medium to another, causes that bending. So refraction is really due to the changes in the speed of light as light goes from one medium to another. That's why refraction happens. So when we talk about the speed of light, we often represent concept of the speed of light using a number called the index of refraction. The index of refraction is represented by the symbol n, is a number that tells you how slowly light travels in a certain medium compared to space. So for example, let's say I had n is equal to 2. What that means is that in this medium with n is equal to 2, so let's say it was medium A and it has an n is equal to 2, index of refraction of 2, in that medium, light travels 2 times slower than it does in space. Let's say I had n is equal to 2.42. What this means is that in this medium, light travels 2.42 times slower than it does in space. So the higher the index of refraction of a medium, the slower light travels in that medium. The lower the index of refraction, the faster light travels in that medium. The fastest that light can ever travel is going to be in space, which is 3.0 times 10 to the power of 8 meters per second. That magic number you need to remember, this is the 3.0 times 10 to the power of 8 meters per second, or 300 million meters per second, is the speed of light in space, where there are a few particles or very little particles that will slow down light. So that's the fastest it can travel. As soon as it gets into other media, it slows down. So the formula to calculate the index of refraction is written right here. It's the speed of light in a vacuum. A vacuum is just another way to say space, where there's no particles, divided by the speed of light in the medium that you're trying to study. So speed of light in a vacuum divided by the speed of light in the water would give you the index of refraction for water. Speed of light in a vacuum divided by speed of light for diamond would give you the index of refraction for diamond. So let's examine that formula in a bit more depth. Here we have the formula written out mathematically speaking. N is equal to C over V. N represents the index of refraction of the material that you're studying. So it could be N of diamond, N of water, N of air. And C represents the speed of light in space, which is 3 times 10 to the power of 8 meters per second. So this is something you need to remember. C will always have the same value. It's a constant, meaning it's always going to have the same value. It's not going to change in our formula. So we're always going to have one known value at least, and that's going to be our 3 times 10 to the power of 8 meters per second. V is the speed of light in the medium that you're studying, the speed of light other than, let's say, space. It could be the speed of light in water. It could be the speed of light in diamond. And so the idea is, in problems involving this formula, you'll have either C and V to find N, or you might have N and C to find V. And so we'll do some practice problems where you have to rearrange the equation, or where you have to use the equation as is in order to solve for some unknown variable. Physics will be full of calculations. You need to know how to manipulate equations, but also how to understand the equations conceptually speaking. So very quickly, on that same note, we have a little question here that I expect you to be able to answer, and I want you to try to answer it using the formula. Could the index of refraction of a medium ever be less than 0.5? Explain. So we know that the formula for the index of refraction is N is equal to C over V. So could the index of refraction of a medium ever be less than 1? For example, could it be 0.5? Could it be 0.8? Explain. So I told you guys that C is the speed of light in space. It's the highest speed that light can achieve. For an index of refraction, N, to be less than 1, so 0.8, 0.5, 0.3, whatever, V would have to be higher than C. If you have a lower number on top of our fraction or division over here, and a higher number at the bottom, that would give you a decimal less than 1. However, you know that C is the highest speed that light could ever achieve, and that's in space. So in reality, the highest value for V would be in space. So really the lowest number you could ever get for the index of refraction would be a case where you have C divided by the speed of light in space, which is C. C divided by C, it's like saying 2 divided by 2 is 1. So the lowest index of refraction that you can get is actually 1. That's just basically saying the speed of light in this medium is as fast as it is in space, which you'd only really see in space. You wouldn't see it in other media because all the particles slow down light. So another concept to briefly mention, when you're doing your calculations, you'll have to show your units. So whenever you're figuring out, let's say, V will always be in meters per second unless stated otherwise. And the index of refraction won't have units, because when you use your formula, N is equal to C over V, C is in meters per second, and V is also in meters per second. When you divide a unit by itself, so M over S divided by M over S, the units cross out. So we say that N, index of refraction, is dimensionless, meaning it doesn't have any units. So again, N equals 1 is the lowest index of refraction that you can get. If you get anything lower than that, then you know that you've made a mistake with your formula. Over here we have a table that has the index of refraction for a variety of different materials. And again, as you can see in space, that's the smallest index of refraction, 1. Everything else has higher indices of refraction. So for example, if we look at, let's say, silicon, it has an index of refraction of 4.01, which means that light in silicon travels 4.01 times slower than it does in space. And kind of like you learned with density, an index of refraction is actually unique to a certain substance. So for example, if you calculate the index of refraction of a substance that was unknown to be 4.01, you can come to this table here and say, oh, then that substance must have been silicon. If you calculate it to be 1.77, then you can come to this table here and say, okay, the index of refraction must have been, substance must have been sapphire. Same thing for crown glass. If you calculate something to be, the index of refraction to be 1.52, then you can come to this table and say, okay, well, the unknown substance that we were dealing with was crown glass. So now we're going to do a sample problem. And to solve these problems, we are going to use the guess method. You're allowed to use a calculator. You cannot use your cell phone. Make sure you're using a calculator and have one ready to use on the day of a test or an exam or a quiz. So in our first example, we have light travels in ethyl alcohol at 2.21 times 10 to the power of 8 meters per second. Calculate the index of refraction of ethanol. And we're going to use the guess method. The guess method is a great way to organize your answers in order to maximize your marks and reduce your chances of making mistakes. So in the guess method, the G stands for our given values. And even though it's not stated in the question, you always know your C value, which is 3 times 10 to the power of 8 meters per second. Another value given to you in the question is this 2.21 times 10 to the power of 8 meters per second. That's your V. That's how fast light travels in the ethyl alcohol. The U is the index of refraction in this case, because we're asked to calculate the index of refraction. The U is the unknown value that we're looking for. So N is equal to what? So E stands for equation. So the equation we need to use is N is equal to C over V. The first S is really our solving. So we're going to do N is equal to C, which is 3.0 times 10 to the power of 8, divided by our V, which is 2.21 times 10 to the power of 8 meters per second. Those are going to cross out because it's one over the other. Because you have 10 to the power of 8 and 10 to the power of 8 over here, those cross out as well. And all you're really doing is 3 divided by 2.21. And that will give you 1.36. So your index of refraction, your solution, is that it's 1.36. So the third S in guess really stands for statement. So our statement is that the index of refraction of ethanol or ethyl alcohol is 1.36. So given values, write down everything that you have given to you or known in the equation, in the problem. Unknown is what you're looking for. So you're looking for the N in this case, the index of refraction. The E is the equation that you're going to use. The S is showing how to solve. The other S is the actual solution itself once it is solved. And then the last S is the statement that you write to show that you understand the problem. So in example 2, we have a slightly different problem, but we're going to use a similar formula. What is the speed of light in zircon? So we need to use our index of refraction table. You don't have to memorize these various numbers here. You just need to know how to use this table. So again, we're going to use the guess method. We have our given value, which is 3.00 times 10 to the power of 8 meters per second. That's our little c. We always know that one. In this case here, even though in the question there's no givens, you can go into your table and find the index of refraction for the material you're dealing with, which is N is equal to 1.92. So that's another given piece of information in our question. So now it's a little bit different in terms of our unknown. For our unknown, we're no longer looking for the index of refraction. We have that. What we want to do is we want to use our index of refraction and the little value, the value for the little c, 3 times 10 to the power of 8, to find V, to find the speed of light in zircon. So our equation is going to be V is equal to C divided by n. All I did is I rearranged the formula. I had n is equal to c over v. And what I want to do is I want to get v alone. I want to get v on top. Right now v is being divided. So if I want to get v on top, I have to do the opposite of a division, which is a multiplication. So I multiply this side by v. The other side where n gets jealous, it also has to be multiplied by v to keep the equality the same. V will cross out over here and over here, because when you multiply and divide by the same number, it's like saying times 2 divided by 2, that just equals 1. Now, you'll notice that when I do that, I have v times n is equal to c. My v is not alone yet. I have v times n. So to get rid of n, since it's multiplied on this side, I have to divide. Now if I divide by n on this side, I have to divide by n on the other side so that it doesn't get jealous. Since I have n over n here, it divides, and I get v is equal to c over n. So that is my overall rearrangement of the equation. Now I can go solve and find my solution. So I do v is equal to c divided by my n. And really all I'm doing is 3 divided by 1.92. And then I'm remembering to put this 10 to the power of 8 back in place once I've solved for that. So I get 1.56 times 10 to the power of 8 meters per second. Now be careful though, because if ever this number is higher than 3, that may change that 10 to the power of 8, so you have to make sure you plug it into your calculator appropriately. What I recommend is when you're plugging these numbers into your calculator, open the brackets first and put this whole number in, 3 times 10 to the power of 8 meters per second. You can't put the units in, but put the whole number in, times 10 to the power of 8. So close the brackets afterwards, and then once you've closed the brackets, do divide by 1.92. If you had two scientific notation problems, I would first put the first scientific notation number in brackets, then do divide, and then the second scientific notation in brackets and press equal, so that your calculator knows that you're dividing two separate numbers. Otherwise, you may get an incorrect answer. So in our situation here, we have v is equal to 1.56 times 10 to the power of 8 meters per second. We can now write our statement, which is the speed of light in zircon is 1.56 times 10 to the power of 8 meters per second. Make sure you put the units, otherwise marks will be lost, because here you're trying to show your communication. You know what we're talking about here. In the presentation, I've included a few more sample problems for you to try. And again, when you are doing these sample problems, you want to make sure that you have this table with you so that you can refer to it to check your answers or to obtain the index of refraction in the case where you have to calculate for v. Same idea with these problems here. Make sure you use your table, use your calculator, practice them, and you'll see you'll go through them pretty quickly. On a quiz or test, you will be provided with this table. So to review, you should read page 515 to 519 and complete the questions on page 519, number 1 to 7. You should also read page 524 to 525 and complete questions 1 to 10 on page 525. There will be some learning goals provided to you. In those learning goals, there's a video, this video here that you're currently watching, so you already did the first step. And you are now able to do questions 3 to 13, which relate to this first part of the refraction PowerPoint. There will be a few other worksheets that are provided to you, so please do practice them. The more practice you do, the better you will be at these problems. And then by the end of the second presentation, you will be able to explain why this effect is actually occurring.